Next, I'm going to discuss a statically indeterminate problem of the clamped bar. A circular bar ACB of diameter d has a cylindrical hole of length x and the diameter 1/2 of d from A to C. So this is the hole from A to C. It is held between the two rigid supports at A and B. A load P is acting in the middle to the right hand side. Assume E is constant and X is greater than L/2, so the hole must be longer than 1/2 of the bar. Obtain the formulas for the reactions RA and RB at the two supports due to the load P. Besides, obtain a formula for the displacement delta at the point of load application. You also have to find for what value of X as RB equals to 1.2 of RA. Well, from what you have learned in Machan 2020 statics, the only formula you can get is RA plus RB equals to minus P, but it makes no sense because you don't know how to find RA and RB by any other things. However, in this course, we are going to introduce you some other equations such that you can find those two reactions. Since A and B are fixed walls, the sum of deformation in sections 1 and 2, so I have already divided this whole bar into two sections in the middle. The sum of deformation is 0 because for this fixed end, when you have a P acting on section AD, that means section AD must be elongated, and consequently, in order to remain the compatibility, the section 2 must be shortened. Therefore, we can write this formula. This is so-called compatibility equation. Next, we find the cross-sectional area of section AC and CB. Notice that the hole is longer than 1/2 of the bar. For section AC, its cross-sectional area is given by 3 pi d squared divided by 16. And for CB, it is 1/4 of pi d squared. Therefore, we can find the area ratio of section AC and CB, which is 3 divided by 4. By those formulas, we continue our analysis. Consider the loading condition on section 1. The axial force in section 1 is RA, but RA is compressive to section 1. Therefore, P1 equals to minus RA. Then, by using the change of length formula, we have change of length of 1 equals to minus RA times L divided by 2E times the area of AC. Similarly, the loading condition in section 2 is in tensile because RB is a tensile force to section 2. However, section 2 consists of two segments with different cross-sectional area. Therefore, we have to divide section 2 into those two segments and find their change of length respectively. So delta 2 equals to this whole bunch of stuff. From previous slide, we get delta 1 and delta 2. Now we can put them into this compatibility formula. Now we add them together to get this formula, and then do a lot of simplification. Also, we try to eliminate the denominator by using the area ratio relationships. Then we can find RA equals to 2L divided by L plus X times RA. For those steps, I try to skip them, and you should try to understand yourself because it is fundamental to engineers. Now, by integrating those two formula, we can solve the system of RA and RB. Then, by a lot of calculation, we find RB and RA. For part B, we have to obtain a formula for the displacement delta at the point of load application. What does that mean? That means when you apply a load here, then you will stretch section AD to the right hand side and compress CD on the right hand side. That means you are going to stretch AD and compress DB. Then there will be a little displacement on the point that you applied the load. Consider the axial strain of section 1. Still, we try to use the alpha formula and we substitute RA into this formula. Also, we put A1, which equals to 3 divided by 16 pi d squared into this formula. Then by a lot of calculation, we can find the delta equals to 8 divided by 3 times P times x plus L divided by x plus 3L times L divided by E pi d squared. For part C, it is rather similar. We just take the result from part A, then solve for this equation. Then we will get the position such that the load of RB equals to 1.2 times RA. Actually, the original problem requires us to also consider the case when x is less than L over 2. However, I wish to leave it as exercise to you because it would be too consuming to do it here. Maybe you can find it in the exercise. Now we change this problem a little bit. The bar is no longer uniform and it will become a tapered bar. The diameter at the left hand side is d, while the diameter on the right hand side is 1/2 of d. Besides, we set that x equals to L over 2, which means this part will become solid. The problem requires us to obtain the RA and RB on the two ends due to the load P applied in the middle. Firstly, since the cross-sectional area of this bar is now changing along the length, we need to obtain the equation for that. Firstly, we ignore the hole, that is, at x equals to 0, the diameter of the bar is d. Besides, at x equals to L, that is, at the end B, its diameter will become d over 2. Since the bar is tapered, the diameter of the bar is varying linearly from x equals to 0 to x equals to L. Therefore, we try to find the linear relationship of its diameter by using this method, which has already been taught in your secondary school. Then, you do the simplification to obtain the diameter, which is minus d over 2L times x plus d. Therefore, the cross-sectional area AX without hole is given by this. Notice that this area is the cross-sectional area without hole. Next, we are going to consider the cross-sectional area with hole. By statics, obviously we have RA plus RB equals to minus P. Besides, since we've already found the cross-sectional area without hole, we can get the cross-sectional area for section 1 and 2 respectively. Recall that for section AC, since there is a hole, we consider the cross-sectional area of the hole, which is pi times 1/2 of d squared divided by 4. Then you can write the cross-sectional area of segment AC in terms of x in this form. For section CB, it is rather similar, but there is no hole. Therefore, you don't need to subtract this term from the A prime of x. Therefore, the cross-sectional area for segment CB is like this. Therefore, by considering all what we have got in the previous slide, we can apply the change of length formula to segments 1 and 2. For segment 1, since this time x equals to L over 2, the cross-sectional area for AC is just the cross-sectional area of section 1. We know for section 1, the force acting on it is minus RA because it is compressive. Besides, we take the constant E out. Finally, we put AAC into this integral, which is very complicated. Similarly, for the change of length of segment 2, since there is a tensile force RB acting on it, it should be positive. Besides, we take the E out and substitute our ACB into this integral. Now we use a lot of mathematical techniques to do this integral. For this integral, we first get rid of the denominators, like this, we try to make the denominator of this integral to be a polynomial. To do this, first, we take the common factor out, which is 1/4. Then, we expand all the terms inside the bracket to get this result. Besides, we take out d squared divided by l squared, such that this will become a polynomial. Next, we do a technique to make this part to be a complete square, and then we can write the integral in this form. Finally, we let u equals to x minus 2l, then dx equals to du, and we will change the upper and lower limits to be minus 2l and a minus 3l over 2. Then the change of length of segment 1 will become this integral. Then we do the partial fraction for this integral. Since it is the difference of square, we can write it in this way. That is, we factorize the denominator, then write them into the partial fraction form. Eventually, by this form, we can write a times u minus l plus b times u plus l equals to 1. How can we get this system? To get system, we first consider this equation. We expand it to be au plus bu plus minus al plus bl equals to 1. That is, since u is the unknown of this integral, we try to sort all the terms with u and all the terms without u, such that we can write these equations. That means the coefficient of u, which is a plus b, equals to 0, while the constant 1 equals to minus al plus bl, which implies that minus a plus b equals to 1 over l. Then we can solve the system in this way. Eventually, we can write 1 over u squared minus l squared equals to 1 over 2l times 1 over u minus l minus 1 over 2l times 1 over u plus l, which equals to 1 over 2l times 1 plus u minus l minus 1 over u plus l. Then we substitute this result into this integral. Now we integrate this integral such that it will become natural log of u minus l over u plus l. The result will become this, which is pretty complicated. So bear in mind that for example D, it is just giving you some basic ideas about some mathematical concepts to be applied in this problem. So as you can see in previous slides, there are a lot of mathematical concepts that you need to do while solving this problem. But the exact place for the application of solid mechanics concept is not that much. That is, you just apply the solid mechanics method here, and all what you are going to do in the future steps is just to use a lot of mathematical skills in order to solve those displacement out. Now, after we considering the delta 1, now we consider delta 2. Similarly, we put the reaction and the E out from this integral and put our area into it. Similar to delta 1, we take out the common factors such that the remaining stuff in the integral will become a polynomial. Then we let u equals to x minus 2l, then du equals to dx, and we change the upper and lower limits to get this integral. Well, this integral is much easier than what we have just solved for delta 1, right? For this integral, it is rather easy. We just integrate it to get minus of 1 over u, and then you place those two numbers into this result, and then you simplify the whole stuff to get this. To express the answers numerically, it will be 1.698 times RB times L divided by ED squared. Finally, we got delta 1 and delta 2 from previous slides. We used the compatibility equations in order to get the relationship between RA and RB. By substituting delta 1 and the delta 2 into the compatibility equation, we can get these very complicated relationships. Then we get RA equals to 2 divided by 3 natural log 5 minus natural log 3 times RB. Eventually, we relate those two equations. So as you can see, this is for statics, and this is from compatibility. As you can see, for statics, we can obtain an equation very quickly, immediately at the beginning. But for the compatibility equation, we need a lot of time to analyze it, to do a lot of mathematical computations. Eventually, we solve the system to get RB is approximately minus 0.434 of P, while RA equals to minus of 0.566 P. In the previous method, we are mainly dealing with the structure by using the geometry compatibility. Now we will consider to solve this problem by using the method of superposition. Now we temporarily remove RB such that this bar has only one force pair, tensile P and RA. Then, for section 1, there will be a tensile load P on it, while for section 2, there is no load acting on it. For section 1, we apply the area of AC, while for section 2, we apply the area of CB. Now, this integral will become 0. Solely consider this integral, we can obtain our results from our previous method. Previously, when we are looking for the delta for section 1, we got this result. Now, we just replace the compressive RA to be the tensile P. That is 8 natural log 5 minus natural log 3 divided by pi times PL divided by ED squared. Now, we remove P and place the RB back. When we put RB back, since RB is tensile to the entire section, we put RB in both integrals for AC and CB. For section CB, which is section 1, we put the area of AC, and for section CB, we just put the area of CB into it. By what we have just found, for section AB, we just put those two results together. Finally, we use the superposition compatibility equation. The deformation caused by P, which is going rightward, right? Plus the deformation due to RB, which is compressive, must be compressive. It should be 0. By combining both the results and the compatibility equation, we do a lot of mathematical calculations, such that we can get the result, which is exactly the same to the previous one. In previous example, we dealt with continuously changing bar, which applying this formula. In this formula, AX has a variable X. However, in this case, we are going to deal with another case. Delta equals to Px dx divided by EA from 0 to L. That is, the force, the direct force inside the bar will become a variable of X, while area will become the constant this time. Let's read this problem. The bar is now rotated in a vertical position. Load P is removed. There is no P inside. It disappeared. The bar is hanging under its own weight. Assume the bar is drilled to the middle. Obtain formulas for the reactions RA and RB at supports A and B respectively. In this case, we can see the area for the two sections are both regular. The area is constant for both sections. However, the P, the tensile or compressive load, will be a variable of X. Firstly, let's still consider this problem in terms of statics. We know that those two reactions are going to support the weight of the whole beam. Therefore, let's try to find the weight of the whole bar. It is given that X equals to L over 2. That means the total volume of the bar is the total volume of the entire bar, which is not drilled, minus the volume of the hole, which is located here. Then, by a series of calculations, we can have the weight of the bar is 7L pi d squared rho g divided by 32. Finally, by statics, we can only get this equation. That is, RA plus RB equals to 7L pi d squared rho g divided by 32. As we know, when x equals to L over 2, this part is solid. Also, the weight of the drilled lower part, that is, for x equals to L over 2, for the material below this level, it is drilled, it is hollow. And for the material above it, it is solid. The weight of the drilled lower part can be calculated in this way, and the result is 3L pi d squared rho g divided by 32. After considering the statics of this entire structure, now we have to consider the solid mechanics part of this problem. The load RB is pulling the bar upward and try to elongate this bar, while the weight inside the bar will compress this bar, so the bar will become shortened because of the weight. So now we conclude that, okay, RB is pulling the bar upward to its original length, while weight itself is tending to compress the bar so that the bar will become shorter. Therefore, we need to consider the deformation caused by each weight independently, which is the method of superposition. First, we remove RB from our analysis, and B will become a free end at this moment. So we completely forget about this, forget about him at this moment. So now this bar has a free end, B, which is here. As we can see, since x equals to L over 2, that means in the middle of this bar, this part will become solid instead of hollow. Next, we consider the cross-section below this level, below L over 2, and above L over 2. For any cross-section below L over 2, all material above this level will compress the material below it, so that there will be negative deformation. That is, the material here will compress this level downward, and there will be compressive load caused by the weight to compress this bar. Now consider what is the weight, what is the load acting on such level of x. We know that the weight of material above this level is given by the weight of the entire bar minus the weight below this level. That is, the weight is the total weight. That is, the compressive load caused by the weight, Wx, equals to the total weight of this bar minus rho g times the volume of the bar below this level. Recall that the cross-sectional area for section AC would be 3 pi d squared divided by 16. Therefore, the compressive load caused by the weight in segment AC, expressed in x, is given by the total weight of this bar minus rho g times the cross-sectional area times x. So we can treat this part as the volume of material which is below the level of x, and the volume times rho g will be the weight of material below this level. After we do a lot of simplifications and take out the constants out from the expression, we can get the compressive load for any cross-section located at position x in segment AC equals to pi d squared rho g divided by 32 times 7L minus 6s. Similarly, for the interval from L over 2 to L, we can find the compressive load caused by weight for a cross-section at level greater than L over 2, say this one. Then the compressive load caused by the weight in segment CB of this bar will become the total weight divided by the weight of the lower half, which is WL over 2, then further minus the weight of material in this region. The result will be pi d squared rho g divided by 4 times L minus x. Still recall that we have already removed RB, for instance, for our analysis. Now we have the compressive load in sections AC and CB. Now we will account for the deformation caused by weight itself. That is, without RB, the bar will become shortened by its own weight. So what is its magnitude? So we need to calculate it. Notice that the deformation caused by the weight is negative, and it is negative of the compressive load dx times the Young's modulus times the cross-sectional area of AC for 0 to L over 2. So from 0 to L over 2, its cross-sectional area is AAC, and the weight for any cross-sectional area and the compressive load for any cross-section in this section will become WACX. Similarly, for the deformation from L over 2 to L, we have WCB dx divided by E times the cross-sectional area of CB. And then we substitute our results here into this expression. We take out all the possible constants from this integral. Similarly, for this one, put it in. Then we do a lot of cancellations in these constant terms. At the same time, we integrate the linear formula inside the integral to be like this. At the same time, we substitute our lower and upper limits to get the result. We simplify the result in the last page to get that the deformation caused by the weight itself is given by minus of 7 rho GL squared divided by 12E. Next, after we consider the deformation caused by the material weight itself, we will consider the deformation caused by RB. So now we ignore the weight inside the bar and we only consider RB. For RB, it is rather similar to what we just computed. For section from 0 to L over 2, we substitute RB and the AAC into the integral, while for L over 2 to L, we substitute RB and the cross-sectional area will become ACB. Then we take out the constants. We leave RB inside the integral, but you know RB is just constant, and the constant dx will become the subtraction between the upper and lower limits. Then the result will become 14 RBL divided by 3e pi d squared. This is the deformation caused by RB. By integrating the deformation caused by each force, the deformation caused by weight, and the deformation caused by RB, by using the superposition compatibility, which means the deformation caused by the weight plus the deformation caused by RB should be 0 because B is a fixed end, which means the length of the bar is not changed at all. This yields this superposition equation. In another word, to proceed our problem, we just add those two stuff together, which yields this part. Then we do some simplifications to get the reaction at B, which is rho GL pi d squared divided by 8. Finally, we use the equation of statics found previously to get the reaction at A, which is 3 rho dl pi d squared divided by 32. Let's do some closing remark of example 2.2. You should have learned a lot from this example, as there is plenty of calculations involved. In this example, we tried to use two kinds of compatibility to solve the problem. One is the geometry, one is the superposition. Both methods are available to use in your exams or in your daily applications. Depends on which one is easier for you. A and C are more common in our exams, as their calculations are easier, because for D and E there are a lot of integral. Sometimes it is very difficult to set some problems for it. But I can just say, in my offering, in my year, the continuously changing bar is not tested. But I'm not sure whether it will be tested in your offering, so still I recommend you to learn about it. in problem D, the cross-section is changing along x. That is, for the integral delta equals to p dx e ax. In this case, ax is a function of x. That means you have to integrate this function with respect to x so that you can find the deformation. For problem E, ax, although it's not a function of x, but p is a function of x. So for problem E, you should use this formula. The deformation equals to integration of px dx divided by ea. Actually, in our real life, all those letters inside can be variable of x. For example, the delta, in the most complicated case, will become the integral of px dx divided by ex ax. Yes, sometimes it is very complicated, but in our practice problems, we try to use only one of them to be the variable, such that we can set the problems easier and we can let you solve the problem in a reasonable time. So, in problem E, the axial load becomes the function of x. In another word, notice that for delta equals to PL over EA, the application of this formula has a lot of restrictions. For example, the load should be uniform, which means P should be constant. Besides, the bar should be prismatic, which means we don't accept a bar like this. For this bar, you can also say, okay, the cross-sectional area are the same, but it is not prismatic because, as you can see, there is a bowl in the middle. A typical prismatic bar is like this. The bar has a center line for all cross-sections. And also, the cross-sectional area should be uniform, otherwise a will become the function of x and we need to do the integration. And very often, we assume e to be constant,